We are discussing about Bayesian learning, and we have seen that there are two types of learning scenario under this particular uh, scheme, particular framework. Of course, when we say Bayesian learning, we consider mostly that we should compute the posterior of a hypothesis given the data. That means probability of a hypothesis given the data, or we call it posterior of a hypothesis. But also under the same framework, we also consider another approach where we compute the likelihood of occurrence of data given an hypothesis. So in both the approaches, we are trying to maximize these probabilities. So the hypothesis which maximizes this probability, that hypothesis is selected. That is the kind of decision process. But there are also some other variations. We will discuss that part later on, today's lecture itself. So let us understand what are these features of Bayesian learning. So the example what we discussed in the previous class, and we can see that it's a very flexible learning framework in the sense that for each observable instance, it can modify it influences the decision process, because given a new observation, the probabilities of data and also probabilities of likelihood of data, those are those change, right? So the prior definitely remains the same, but these two probabilities, they can be recomputed, or you can given the new instances, you can update them, and accordingly your decision gets also updated. So it causes either increasing or decreasing of a probability in its particular context, whether it is posterior or whether it is likelihood for the selection of a hypothesis. And the other feature, as I mentioned, and we have seen that this prior knowledge of hypothesis, which is the prior probability of a hypothesis in the hypothesis space, that is the preferential, preferential bias that is being taken as an inductive bias in that case. So that is there, and it accommodates hypothesis with probabilistic predictions that we have discussed. Finally, you are computing a probability, and based on those probabilities, you are taking a decision. Here, the interesting thing is that that's what I was telling you, that we can have also the other variations of taking a decision. Rather than considering a point decision, that means the hypothesis where you get the maximum posterior or maximum likelihood, what we can consider a decision which is weighted by these posteriors. For each hypothesis, you may consider that there is a decision, and then you can do that. So we'll see that. Then provides a framework of optimal decision making. That this is what that optimal decision making takes place if you take that kind of weighted decision. And sometimes the computation may not be feasible, because you have the huge hypothesis space, but it provides a framework which can give you that what should be the ideal situation. So let us discuss a few some of the things what we have already considered under this Bayesian framework, that we have discussed particularly the concept learning. We'll be considering now that how concept learning, that particular computation is also related with this kind of Bayesian decision process. So as you see that while taking a decision in this Bayesian framework, you need to compute these three quantities, particularly if you are going to compute the posterior. So the first thing is that you need to compute likelihood, and then of course there should be a prior. That kind of modeling should be there of the prior, and of course, and again you have to compute the probability of data. That is, we call marginal probability of data. So in the concept learning, if we remember that the process what we discussed there, we assume that likelihood of a data given an hypothesis, if there is, say, if the hypothesis belongs to the version space, so it is with probability 1, because no, our assumption is that there is no error in data. So if the hypothesis is true, and since there is no error in data, training error examples, so this data will be observed if the hypothesis is true. So otherwise, that is what is the definition of a consistent hypothesis. So version space consists of all set of consistent hypotheses. So that's why this probability should be 1. This likelihood of data given that consistent hypothesis should be 1. That is the definition itself of consistent hypothesis. Otherwise, if it is not a consistent hypothesis, it is not a member of a version space, then this probability would be 0. So this is the likelihood computation goes in this way. And whereas if I consider a prior, one of the standard thing is that no, you consider uniform distribution. That means without any bias, without any kind of preferential bias, you assume all hypotheses are equally probable. So it depends upon the size of the version space. That gives some kind of weight of choosing certain hypotheses. So as you can see that if I consider this is of having uniform probability, and if the size of the version space is given by these set cardinality operations, that means H is the set of all hypotheses, is the hypothesis space. So cardinality of this set, which means the number of elements in that hypothesis space. So 1 by of that number should give you the probability, uniform probability for a particular hypothesis. That is what is the modeling of a prior probability of a hypothesis. And then if you compute the probability of data, that means what is the probability of the occurrence of a data, that is interesting. And as I told you, this marginal probability of data is the major, I should say, one of the challenging task in this computation. So let me know from you that what do you think? What should be marginal probability of a data? See, if you observe a data, so what is the probability of a data? How do you compute it? Can you think?
Fraction of the positive.
Sir, summation of PD by H times PH.
Pardon?
Sir, summation of this probability of likelihood times the probability of prior.
That's right. That's right. So for all hypotheses, you should do, right? So summation of that. So yes, you are right. So sum of this probability of product of this likelihood and prior for every hypothesis over the hypothesis space, and that would give you the probability of data, right? So what should be this value?
Size of version space divided by size of hypothesis.
Size of version space divided by mod H.
Right. Yeah. So so this is the derivation, because you see that if you consider a hypothesis in the version space, then its likelihood of the data is 1 because there is no error in the data, right? And then of course 1 by mod H, 1 by cardinality of H, that is the prior probability of any hypothesis. And if the hypothesis is not in the version space, then the likelihood would be 0. So there are this many hypotheses which will be produced, which will be contributing 1 when you are computing this likelihood term. that is equal to the number of hypotheses in the version space. So finally, you can see the probability of data is also constant. Any data, if you consider, that is no, sorry, it's not constant, because now version space is dependent on data. I'm sorry. So it is size of the version space divided by the cardinality of the hypothesis space. Any confusion? So with this, if we compute the probability of hypothesis given data, that is the posterior, so you get this. It is 1 by version space, 1 by of the size of the version space. If the H is in version space, otherwise it is 0. So narrower the version space, higher is the probability. And in the more, I should say, extreme case, if you can narrow it down to a single hypothesis in the version space, only that is the hypothesis that would satisfy the data. And since there is no training error, you have only one hypothesis to consider as a target function. So it should be with one, that should be, output of this computation. So that should be selected. So now let us consider another scenario. And many of you know this, that you can use this technique, that least mean squared error estimate of certain model. Suppose you are going to model a target function. So you have the model, you have the form of a target function, and you have a set of observations, and say yi xi. This is a set of observation, and this hypothesis H. You choose any H. H is the kind of your approximation of that model. That is the hypothesis you are considering. So from the H, you are trying to get the target function. So H is trying to approximate the target function, or trying to represent the target function. I should say, giving you the target function. So you can always represent in this form, and you are assuming here noisy data. So in the previous case, when you are doing concept learning, as you see that we no training error, but now we are assuming that in your observation, we are allowing that there could be error in your observation. So EI is the error part. So HXI gives you the value of the target function. So you consider it's a numeric in the numeric domain. So your y is a value, maybe in either it's integer or in the real domain. So you take it a numeric value, and xi is your input instance, and which could be multidimensional input instance also, and in which could be a real space element of a real space, or you may consider also some discrete attributes in this case. But normally in this kind of least mean squared error, we consider it's a regression analysis where we consider there from the numeric domain. So if you consider that, so the modeling of this error is very important. And in many cases, in most cases, I should say, or if you do not have any other information, we usually assume this error, they follow a normal distribution. So this is the mean square error expression, that when we are, what is the sum of square of these errors for each data instance, for each observation. So is it clear? This expression, mean squared error expression, you consider each observation, ith observation, and you find out what is the error of observation, take the square of error and sum of square of error. So of course mean is not computed here. So I should have written SSE here, sum of squared error. And if you consider mean, it has to be divided by n. Okay, since it's just a proportional term. So with respect to this particular, in this context, it is okay. But this definition is wrong. I have not divided it by n. So it is not mean. It is just sum of squared error. Now, there I was referring at that error could be modeled by a normal distribution. So what does it mean? What this distribution means?
Zero.
Pardon?
Zero mean normal distribution with deviation sigma.
Right. Zero mean is sigma. So it is quite intuitive, isn't it? That means average case you are assuming that your observation is approximately correct, right? There would be on the average it is very near to the true value, which means it is very near to the true value. So you have an error which will have many a times the value would be very close to zero, or we consider that is what average. If you take the average of few instances, it would be mean would be this error mean would be zero. Mean of the error should be zero. Whereas there would be variability. So that depends upon how consistent is your measurement. So there could be also how reliable is your measurement. So if your measurement is not that much of reliability, so this error range could be quite high. So sigma denotes that standard deviation, as you mentioned, and in a normal distribution, you can very easily capture this particular probabilistic random, this kind of probabilistic modeling of a random process. That means the error, right? So can you tell me that what is the expression of this particular distribution? It's a Gaussian distribution. So n denotes it's a Gaussian distribution. So it's a particular distribution. So what is the distribution?
So 1 divided by under root 2 pi sigma square e raised to power x by 2 sigma square.
I hope everybody understand that, as he has mentioned, it is basically if I exponentiation of that minus half x squared by sigma square, and it has to be normalized by root 2 pi sigma. That means 1 by root 2 pi sigma into e to the power minus half, then x squared by sigma square in the exponentiation whole terms comes. Is it clear? I'll be showing you the expression itself. Okay. So now if I consider the full observation, that means if I consider the observation yi, and if the model is hxi, that means the model is also given to h, and the observation is also xi. Sorry, instance is input instance is xi. So what could be the mean of that observation? Mean of yi. So how yi should follow a distribution? What should be the distribution of yi given this error distribution?
Mean would be h of xi, and
Very good.
variance would be same.
Very good. So if I consider, let me use this. So as you have rightly mentioned, it means that this distribution will have, for yi distribution, we will have, I can write in the same format, that mean is hxi, comma, and then variance is sigma square, or standard deviation is sigma. Is it clear? So this is what is your yi distribution, right? Is it clear now? Okay. So now you tell me then, what is the likelihood of data? So what is your data? Data is this n observation points, yi, xi. Okay. So what is the likelihood of data if you consider every observation is independent, right? Every observation is independent. So what should be the likelihood of your data? That means I would like to compute probability of D given H, right? What is the likelihood of it?
So
Yes.
product of all the individual yi's which will be Gaussian. Yeah,
Very
product of I equal to 1 to n.
Very good, very good. That's what I'm also writing here. Can you see that? Right? Product of all these individual Gaussian distribution. Okay? So we can always get an expression for that. So let me see. Oh, I am always choosing. Uh, uh, right. So as I was saying, same. So what is the probability of? So this is the expression you get. Is it clear? Is sigma should be within square root or it should be outside? 1 by root 2 pi?
Sigma should be outside.
Outside. Yeah, that is an error. Okay. Please note this thing and we may correct. So you see that this is you get as your probability of data given hypothesis. Is there any confusion among anyone? This is how we compute the likelihood function. So the thing is that actually mean square error problem, what do you do in the mean square error estimate? It is a list you are, so the hypothesis which is giving the list mean squared error or sum of squared error, whatever way you can say, right? So it is a minimization. So the H which will minimize that expression of MSE.
Sir,
Yeah.
sir, when you are taking that constant term 1 by root over 2 pi sigma square outside the product form, shouldn't it be multiple? I mean, raised to the power of n?
Yeah, it should be also power of n. You are also right, but that's a constant term. That's correct. So there are multiple errors in my expression. You are right. Thanks. So maybe my subsequent expressions would be also wrong in that case. I overlooked this. So let us see. But what we do, we take the log likelihood, because why the logarithm? So minimization of this, maximization. It is a maximization problem now. So this is the likelihood, isn't it? So what you need to do, you have to maximize this probability with respect to some h. So h which will maximize this, I will select that. Now, you know that this also is equivalent if I maximize its log, because logarithm is a monotonically increasing function in the positive axis, along the positive axis. Okay. So you have this. So this has to be, so the first term there has to be corrections, as I mentioned. That log of 1 by root 2 pi sigma is not correct here because of that expression itself needs modification. But you observe the second component, that minus sum of all these things. So can you see that how it is closely related with mean square error, and when it is closely related?
When variance is 1 by 2.
Yeah, sigma basically 1, but it is not required. Variance is also a constant, isn't it? Sigma also have taken as a constant. So if I minimize this expression, means I will minimizing that expression itself. So HML can be considered. That means the hypothesis which will maximize this likelihood. I denote it as by HML. In this case, the subscript ML will be used. So it is given by this expression. So this is, again, you see that actually mean squared error estimate is modeled under Bayesian framework also. You can get the similar modeling.
Sir.
Yeah.
Sir. Sir,
Yeah.
can you please explain the likelihood part? I could not understand how this formula came.
Which one you could not understand? This product?
P of D given H. Yes,
Yeah.
sir, the formula.
So, if I actually I will be asking you some questions to understand why you did not understand. So, what is the probability of a single observation YIXI?
Yeah, so that is given by the normal distribution of
That is
n of hxi comma sigma.
very good. That is given by that. Okay. So now you consider all observations are independent. So what is the probability, joint probability of all observations?
Okay. Oh, okay.
So is it okay now?
Yes.
Okay, fine.
So the underlying assumption is that this is identical and independently distributed, right?
That's right. All
IIT.
That is the underlying assumption. You are correct.
Thank you, sir.
So next, let me proceed then. So let us consider another scenario. So here we are considering the minimum description length principle. We have discussed also that while choosing an hypothesis, you have considered several competitive scenario for taking this decision process. Particularly in the decision tree, this description length principle we have discussed at some point. If you can remember that when you are pruning a tree, then you are trying to see what is the size of your tree and what is the size of the examples which are not really matching with, because it is pruning, so which are not consistent. I mean, which are not consistent with that model. Examples where you are getting error. So if you consider them to consider them as an exceptional cases and store them separately so that you can always first consult them and then you take this decision using decision tree. Then what is the size of that example set? So sum total will give you the size of that particular model. That means hypothesis come those exceptional cases. And what is the size of the full tree? Because in the full tree you are assuming it is consistent. There is no exceptions. So if you find your size is less, then you are chosen. If you remember, that was the kind of decision process we have discussed. Now let us see that this particular Bayesian decision theory, that is, you are considering this map approach, where you are choosing that hypothesis which is maximizing this product of likelihood and prior. I'm not saying here posterior, but actually you are maximizing also posterior given the data set. So I would once again, I will separate them out using logarithmic operations, because as I mentioned that this kind of, since logarithm is a monotonic function, so maximization, minimization, all these operations, they are applicable in the log domain appropriately. And if I consider the negation of that, we are trying to take the argmin of this. Okay. Is it clear? This equivalence, mathematical equivalence, is it clear? Fine. Now can you tell me? Yeah, some question?
Sir, how will we calculate P of H?
No, we are not calculating P of H. How we are calculating P of H is not, we are not discussing. We assume that there is a distribution given to you, P of H. We also assume there is a distribution, somehow you have computed P of D given H. We are not discussing how we are computing. We are trying to show that how this decision process is also is also can express the minimum description length principle. So that is also accepted by Bayesian framework, under Bayesian framework. Okay.
Okay.
So you see that you get this expression. Now, can you tell me that what it is? What are these things from the information theoretic point of view? what is minus log 2p of it?
Entropy of the hypothesis.
Yeah.
Sir, expectation.
Number of
because-
bits required to encode the
Yeah.
data.
Yeah.
That is what. I mean, it is basically the average number of bits required to required to represent a hypothesis.
Sir, but
It is also-
entropy's formula was P log P summation, right?
Yeah, I mean, that is what. I mean, it is a particular hypothesis. If you consider a particular hypothesis, it is considering that only. So that is the average representation. But when you consider particular minus log 2ph, it is the size of that hypothesis. That is the information theoretic representation. So lower the probability, you require higher size to represent it. For the efficient transmission, so there are some other underlying, I should say, objectives. So this is giving description length of optimal encoding for a hypothesis H. That means optimal encoding says that for every hypothesis, its size should be proportional to this. Then the average hypothesis, average size would be that entropy. Okay, its size should be this, I should say. And the other one is the description length of optimal encoding for, again, data given hypothesis. Right. So this is how this minimum length principle under this framework you can consider. So I have once again I have mentioned this information theoretic interpretation of particular entropy, and you can see that. So these are the three scenarios I have discussed after Bayesian discussion Gradation framework. One is concept learning. The second scenario is mean squared error, where actually you are considering maximum likelihood based approach. And third scenario is again the posterior based approach, where you are minimizing the length of your hypothesis. Now, the fourth scenario is that how under Bayesian framework you can actually design an optimal decision making process. So that is very interesting. See, when you are learning a target function under this probabilistic framework, actually you can make it this prediction optimal. So you consider a target function where the instance space is X and your labeled that is set of possible class levels are V. Now this is the kind of target functions we are considering. We are assuming your range, the target range, it's a finite range, and there are discrete values, and they are class levels. So it's a kind of classification problem we are considering. So we are discussing optimal classifier. So we are discussing with respect to the classification problem. And given a hypothesis space H, so every hypothesis in that space, it provides you a function mapping from your input space to these class levels. And one of them may include, in the hypothesis space, this target function may be included. So every hypothesis has certain probability of having some commonality with target functions, some agreement with target functions, and some disagreements with target functions. So usually the hypotheses which are mostly agreeing with a target, but that we only consider only observed samples. So in the general case, what should be the scenario? That is a kind of predictive, that kind of thing we just predict. We consider the analysis of that kind of I should say that from the training examples, as you see, that validation set, test set that we have created because of that only. Anyway, so let us focus to this, consider this discussion, that under this scenario, we say the map hypothesis, that means the hypothesis which will be chosen if you apply the map policy, maximum a posteriori principle, then this is the principle. That means the hypothesis for which this posterior is maximum, we choose that hypothesis. Now, it may not be always in agreement with the target function, as I was mentioning. So there is certain probabilities by which it will have some agreement with target functions, right? So it may not be always consistent with respect to target functions. So it may not be optimal. That means there could be some combination of hypotheses. If you consider there are in certain cases there are some other hypotheses which are actually providing you the actual answer, or which are giving you the true value of the target functions. Now you consider a decision making process where this particular decision of a hypothesis, what is that decision? Decision is that what is the class of that instance? That means this functional output, that is the decision. Now, which output you should take, that should be weighted by their posterior. Okay, so which means you find out what is the probability of a class level given a hypothesis. So that is what you are modeling. What is the probability of a class level given a hypothesis? If you model that, then you consider the weighted average of all these probabilities where weights are given by the posteriors. And you take that decision, that level where this weighted combination is maximum, instead of taking blindly the decision of the map hypothesis. So it's a kind of ensemble learning, as you can see. And this can be shown that it is an optimal classifier in the sense it will be minimizing the error of classification. It will be minimizing the error of classification. So it can be shown. And in fact, so that's what. But the problem is that sometimes it is intractable. I will come to that. So let me take this as an example to illustrate this. So we'll be considering a very simple case. Let us consider our hypothesis space has only 3 possible hypotheses: H1, H2, H3, and there are only 2 class levels, positive and negative. And given a data, some data you have been given, and you have computed all the posteriors, and which have been computed as, say, those values are shown here, right? As you can see, probability of H1 given D is 0.4, probability of H2 given D is 0.3, and probability of H3 given D is 0.3. You note that sum of all these posteriors given that data, that should be equal to 1. So in the whole hypothesis, if you consider all the hypotheses you consider given a data, sum of all posteriors, once again, that should be equal to 1. So that is what was the normalizing factor, that probability of data we discussed earlier, if you remember. Now, what should be the maximum a posteriori hypothesis? I have already shown. I hope it is clear in this case, because there is no competitor. No, sometimes it may be ambiguous, but in this example, it is the hypothesis H1, right? So, and also I will give you what are the levels each hypothesis is given an instance. Suppose you have an instance X, and given that instance, these are the levels this hypothesis they compute. I mean, here it is computing in the crisp terms. That means it's not probabilistic model in that sense. It is put into probabilistic framework in this way, that probability of positive given X under hypothesis H1 is 1. Similarly, probability of negative under hypothesis H1, that means and given X, it is 0. Okay. Similarly, for H2X also, there the probability of the negative under H2 given X should be 1, and probability of positive under H2 given X should be 0. So in this way, there are 2 discrete probabilities, one for positive, one for negative, given that instance X. For every hypothesis, it is either 1 or 0. Is it clear? This is the probabilistic model. So now if I compute, so as you can see that what should be the H map X in this case? It is positive because you are taking just that instance only. But if I consider that ensemble computations, that means weighted average, weighted leveling, weighted decision, weighted probabilities of any level, then we can see that we are trying to find out the. I have written all the expressions together. So since there are only two classes, positive and negative, so I have considered all the products of, products of all the probabilities of that level given that hypothesis and also the posterior. Let me use a pen just to explain the components. See, this component, it computes the probability of a level of the level positive given that instance X, considering all the hypotheses. Okay, posterior hypothesis. Is it clear? In combination. Similarly, this is computing that what is the probability of that instance X is in the class negative, once again considering all posteriors of the hypothesis. So if I compute these two terms, what we get, as you can see, that this term is this one, because probability of positive given H1 is 1, and what is probability of what is the posterior of H1? That is 0.4. And rest of the components, all these components, they are all 0, because their probabilistic model of their levels for under those hypotheses, the probability of probability of level positive is 0. Okay. And what about for the consideration of the negative level? For H1, naturally this is 0, but for H2, since it levels it's negative, the probability of the negative level is 1. And then you have its corresponding posterior 0.3. Similarly, this is the probability of level negative given H3 is 1 and its posterior is 0.3. So finally, you see that you have these two probabilities of levels positive and negative given that instance, in that considering the contributions from all the hypotheses weighted by their posteriors, right? So it is the weighted probabilities. And where it is maximizing, which one is maximizing? This one. Which decision gets maximized? Under which decision? Which level?
Negative.
Negative level, right? So what should be your decision in this case? As you see, sorry, see that this is the difference. If you consider the map approach, you get a point. I should say it's a decision at the particular hypothesis. You are ignoring the contributions of all other hypotheses. And if you consider this kind of approach, where ensemble kind of computation of the probability of a particular level, considering contributions for all hypotheses, then it is a bit different, and it is more. It can be shown that it will have less error than the map hypothesis with respect to that target functions, error of classifications. But as you can see that this computation is very exhaustive. It's an exhaustive enumeration, so it is not always possible. If your hypothesis space is infinite or very large, even if it is finite, if it is very large, so it is not always feasible. It is interactable in that sense. So that is why you cannot always use this method. Okay, but it gives a framework. That's what it says. That's what I mentioned. Now there is another interesting approach which also considers a kind of this ensembling principle, but instead of enumerating exhaustively, it chooses some kind of greedy policies. What kind of greedy policy? Probabilistic greedy policy, I should say. So what it does, it chooses a hypothesis randomly for an instance X with posterior distribution probability H given data. That's all. And you choose that. So naturally, the map hypothesis, which has the maximum posterior, it has the maximum chance of being selected. But it is not always true. It is not always true. It can select also some other levels. Now you can make some kind of combination of this Gibbs algorithm, but this is what is Gibbs algorithm. It's very simple. It just makes one random choice. That's all, and use that hypothesis to get the class level. Now you can think about some other variations. That's up to you. But it performs suboptimally, and it can be shown that if you use simply this particular technique, it can be shown that expected error at most twice of the optimal error when the prior has uniform distribution. So this is a very good theoretical result about this. So just to summarize, particularly this Bayesian classification concept, this decision-making process, as you can see that you have an input which is a training set of tuples and their associated class levels. So that is the kind of data you will have. For example, you can represent each tuple by an n-dimensional attribute vector. So in the all my previous discussion, I have just simply represented by one symbol, but you should consider they are actually n-dimensional attributes. So, and let there be m classes. So what is your objective here for Bayesian classification? You have to derive the maximum posteriori, that is the maximal probability of Ci given X, and which means you need to compute these particular components. And as I mentioned that given X, you may not compute the denominator. It is just the product of prior and likelihood that is sufficient to be considered, and that needs to be maximized. I think with this, let me stop here today, and let me first download your attendance. Okay, I hope the attendance is downloaded. So if you have any question, let me know. So I understand there is no question. So tomorrow we will be meeting in the early morning class at 8. Okay, thank you very much. So I'll be stopping this recording.